My name is Zhenyu from University of Virginia. Today, I'm going to talk about recovery failures and how we expose them by simulating recovery actions in production distributed systems. Failures are inevitable in cloud systems. They often make critical services unavailable and lead to major economical losses. Therefore, correct recovery is critical. When failures happen, failover moves the service to the backup component. Checkpoint recovery rolls the system to a previous safe state. Administrative tools allows the operator to inspect the problem and manually fix the issue. However, recovery often causes bigger problems than failures themselves. They are also known as recovery failures. In Kubernetes cluster, the health probe incorrectly triggers the recovery because of the transient slowdown and consumes more and more energy and finally takes down the entire cluster. Azure's recovery mechanism kept migrating virtual machines to other servers, but each recovery attempt re-triggered the same bug and spread the failures across the servers. Here we show a real-world incident from HBase. HBase is a distributed key-value storage system in which region servers are responsible for storing the data. In the incident, the region server crashed when replicating a corrupted log file stored on Hadoop file system. The coordinator detected the failure and initiated the recovery by failover to another available region server. However, since the corrupted log file was still there, the second region server crashed again when replicating. And this procedure continues in a loop. Eventually, the entire cluster went down. This shows, without the proper checking, recovery can become a deadly source of new failures. So how common are these recovery failures, and why are they so hard to prevent? To answer this, we conducted a study on production recovery failures from 8 popular distributed systems by searching their issue tracker with keywords such as recovery and failover. In total, we collected 75 cases. We found that mature systems still encounter a lot of recovery failures, and they often lead to severe consequences such as service unavailability. Then we ask, can we prevent these failures by targeting at dominating root causes? Unfortunately, our study shows that the root causes of recovery failures are very diverse, such as state management and error handling deficiencies. So there does not exist one bug detection tool to solve all of them. The fundamental challenge of recovery failures comes from complex interactions in the distributed systems, with more than 92% of recovery failures manifest across threads, processes, and even other services. So a good solution should handle all the dynamics. Then, how do we deal with such failures? A natural solution is to prevent them offline. Developers either model the system or use different testings. However, high-level models often miss low-level implementation bugs, and it's hard to expose all the dynamic interactions during offline testing. Another idea is to detect recovery failures online, like A/B testing. We could try recovery on a few machines first. However, the limitation is the few machines we test on do not have the same environment as the rest of the cluster. So even if the test looks fine there, it might still fail somewhere else. And more importantly, we are still touching production environment. So if the recovery is wrong, this small test can lead to cascading failures. Actually, many software have a dry run feature. So can we simulate recovery in production, but with an accurate and safe way? We propose pilot execution. It's a new execution model to simulate recovery in production to validate its consequence. To use it, developers first simulate recovery in production with pilot mode and observe the consequences such as exceptions and timeouts. Based on the feedback, developers could adjust the recovery strategy like updating the scope, and then perform the correct strategy. This idea may sound familiar because in systems, we often use speculative execution. We will run something early, and if it turns out to be useful, we will commit it. But the goal of our model is totally different. In speculative execution, we run early to improve the performance. In pilot execution, we run early to check for recovery safety. Our model also has distinct challenges compared to traditional speculative execution. Firstly, the simulation should not disrupt original system. We isolate the simulation with dedicated and transient threads, and we call them phantom threads. Second, it should be accurate even the recovery involves distributed components. We propagate the tracked metadata across these distributed components and propagate the execution along with metadata for accurate simulation. Finally, the simulation should be fast to avoid delaying original recovery significantly. Instead of making parallel execution faster, we cache some results of parallel execution and reuse them during original recovery to reduce the end-to-end time. Now let us talk about design details. To make parallel execution isolated, some intuitive ideas include transactional rollback and virtualization. However, it's either hard to implement in distributed environments, or it will incur high overhead. So our idea is in Situ simulation. We run parallel execution in live production system for fidelity, but with dedicated threads. And we will explicitly manage these threads and isolate all the side effects. Let me use a previous H-based incident to illustrate how phantom threads are used. In the H-based incident, region server 1 crashed, and the Z node in Zookeeper bound to region server 1's liveness is deleted. This deletion event will trigger the callback function, which is the starting point of the whole recovery process. We identify and then instrument the starting point of the recovery to enable parallel execution by inserting our parallel API calls. This API calls will divert the execution into parallel mode by spawning a phantom thread. The phantom thread executes a special parallel version function which preserves the recovery logic but isolates all the side effects. And this is a concrete code snippet of the recovery process to illustrate how we achieve isolation. Parallel execution will isolate the modification to production states by firstly creating a parallel version state. Then, in the parallel version function, we lazily shadow copy the original states into this parallel version state. Next, we redirect all subsequent accesses to parallel version state. This process will repeat recursively if the parallel version state contains nested objects. We apply the same idea to I/O and third-party service calls by redirecting their operations to the shadow files. Phantom threads may compete with original threads for shared resources. To avoid disturbing production, we use speculative log to let phantom threads always yield to original threads when such contention happens. Since phantom threads may be spawned across the entire system, we need to track and reclaim them to avoid resource leaks. We let each phantom thread register itself when started and deregister itself when finished to the status registry. When all the registered phantom threads are removed, the parallel execution is considered as finished. If a parallel run times out or aborts, parallel API will remove it from the status registry. This will trigger the cleanup callbacks on each node, which will stop and reclaim all the corresponding phantom threads. Also, phantom threads might be spawned indefinitely under some malicious scenarios, and this will overwhelm the system. To protect the original system, parallel API will stop spawning new phantom threads when the number exceeds a pre-configured limit. The second challenge is recovery often cross thread and process boundaries, such as RPC, so we need to handle such propagation for accurate simulation. Our high-level idea is to propagate parallel execution with a tracked metadata. Specifically, we initialize the metadata at the starting point and propagate along the recovery flow. For example, send RPC will also send this metadata to region server 2. And once region server 2 receives the metadata, the receiver side will spawn a new phantom thread to continue the parallel execution. The propagation will continue until parallel execution finish. In our design, we call this metadata parallel context, which involves a globally unique ID as an indicator and span metadata to record the propagation lineage. The good news is that for some common cases like RPC, existing tracing infra like OpenTelemetry already supported. So our instrumentation could directly piggyback on existing tracing infra with some lightweight hooks. Some population cases are tricky, like condition variable, because we need to simulate the affected behavior without affecting original threats. Our solution is, in the offline stage, we instrument the condition variable to be a wrapper that includes a parallel context and record the affected thread. During runtime, a new fundamental thread will be spawned to mimic original thread state for accurate simulation. In normal recovery, thread T2 at region server 2 would crash with a fatal exception, and in parallel execution, we replace the dangerous crash API with a safe report API to send feedback to the operator to help them locate the recovery failures. The third challenge is, since parallel execution adds an extra run before the real recovery, so without any optimization, the total end-to-end time will be more than doubled. Skipping some operations in parallel execution to make it faster will make the result inaccurate. Instead, we cache its expensive I/O and computation results during parallel execution and reuse them when committing the real recovery to reduce end-to-end time. For example, if recovery downloads a file, Pilot will cache the downloaded copy during parallel execution and reuse it in the later recovery after a checksum check. We've described parallel execution as an execution model, but existing systems does not naturally support this mode. Thus, we present our system called Pilot, which will transform the system code to enable parallel execution. Currently, Pilot supports Java systems, but our core design and algorithms are language agnostic. It has two main stages. In the offline stage, the instrumentation engine will transform the original function into a parallel version function, which preserves the recovery logic but isolates all the side effects. At online stage, Pilot library will spawn multiple fundamental threads, which are managed by the state registry. And each fundamental thread could propagate to other nodes with the hooks we added. Now let's talk about evaluation. To evaluate if Pilot could detect recovery failures in production, we reproduced 20 real-world recovery failures across 5 popular distributed systems, such as HDFS and Solar. The failures cover a range of symptoms. We compare Pilot with 4 natural alternatives. Firstly, some systems provide the preview mode, which tells what the recovery plans to change, but it does not actually execute the real path. Secondly, A/B testing. We could try recovery on a few machines first to give us realistic feedback, but it still touches production and is risky. Third, there are some log-based detection tools, such as virtuous cycle detection. They can catch certain types of recovery failures, but they are not very general. Finally, validation slides create a separate environment to test recovery changes, but this environment still differs from production environment. Across the 20 reproduced recovery failures, Pilot detects 17 out of them, where all the baselines combined together detect only 8. Some results of A/B testing is non-deterministic because the result is highly dependent on how we select the test nodes. Where parallel execution makes recovery too slow, to answer this, we evaluate it under 2 settings. In the buggy version, we compare normal recovery with parallel execution. This tells us whether parallel execution could expose the same recovery failure because the system actually performs the recovery. We find that the cost is minimum, with only 3.99%. Then, in the fixed version, we measure the cost when the recovery is actually safe. In this case, parallel execution will run first, and then the system performs the real recovery. Thanks to our caching optimization, the total end-to-end time only introduces 17.63% time overhead. Although Pilot is not designed as a general bug finding tool, it still exposes a bug in the latest version of HBase. Despite developers try to provide accurate information for recovery, in this case, the exception is still swallowed and never propagated to the client. It causing recovery to always be incorrect. HBase community confirmed our bug and merged our fix. To conclude, recovery in production could be risky. We propose parallel execution is a dry run for recovery action. Our evaluation across 5 distributed systems shows that the idea is feasible. And this work represents our first step towards validatable cloud management. Thanks you all. Now I'm ready to take any questions.